An STL file is a way of encoding a 3D object so that it may be shared and printed. Normally, you generate an object in a CAD program and then export it as an STL, which then can be used to generate instructions for your particular printer. Here I am in Fusion 360. This is a part I designed for my time machine. For a project I'm working on. And now say I want to print it, I would have to go here and go to export. And there's some options here, but one of them is STL. And I click on export. Or maybe you want to use a file that's already been generated by somebody else. Often files are shared in STL format. There are other formats, but STL is a common one. So if we look at this classic Stanford bunny, and we open it, 3D viewer. Okay, there he is. There's a bunny. We change the view a little bit, the shading to wireframe. You start to get an idea of what an STL is. You could see that the object is really a mesh of triangles. So even if your original object is very smooth, when you export it as an STL and look at it, again, okay, that looks like a sphere. But if you change the shading to wireframe, again, you can see that the object has been approximated by this mesh of triangles. So the question is, can we make an STL file without the CAD program? Can we make one from scratch? Can we give it our own list of triangles and generate an object that way? And yes, you can. So let's make the simplest STL file we possibly can, and that would be an STL file with just one triangle. Every STL file begins with solid with a name. The name can be anything. It's really not important at all. Begins with solid and a name, and then ends with end solid. In the middle are the triangles, and they have to look like facet, normal. We'll put 0, 0, 0. We'll talk about that more in a second. Then you have outer loop, and then you list the vertices, the 3 vertices of your triangle. In this case, vertex 1 is 0, 0, 1. Vertex 2 is 1, 0, 0. Vertex 3 is 0, 1, 0. And it has to be in this format. The tabs don't really matter. The empty lines don't really matter. Now, let's save it. Save it as. Now we go here. We're not saving it as a text file. We're saving it, let's say all files. We'll call it Chris test and then .stl. Okay. Save. Boom. Now, if we go to 3D objects, we look at Chris test. Let's open it with 3D viewer. And there it is. It's just a triangle. It's just a triangle floating there in space. Wow, that's exciting. Now I've gone ahead and added another triangle. So just the same thing. You have facet normal, 0, 0, 0, outer loop, and here are the vertices to the next triangle. So I'll save it. Go over here, 3D objects, we'll open it. And there, 2 triangles. 2 triangles floating in space. But this is clearly a little silly. You're not going to create a 3D object by entering triangles by hand. So here's an example of how this could be used, a more realistic example. Say I'm tasked with making a parabolic reflector, for example. And I know there are a million ways to do this, but here we'll do it by generating an STL file directly. Using whatever programming language you prefer, we're going to create and fill a text file with the triangles and do it in proper STL format. In our parabolic dish example here, we'll parameterize the dish with R and T. We'll have loops, nested loops going through R and T. T will go between 0 and 2 pi. We're not children. We don't say 0 and 360. We say 0 and 2 pi. And the idea is for any given R and T, like say this point here, we're going to send 2 triangles out. So one triangle will be this one. And the other triangle will be this one. Not drawn very well. Before moving on to the next point. So the next point comes along, you will send this triangle and this triangle. And you can see as you move through the values of theta, we'll fill in this band. Then you move up to the next R and we'll fill in that band, etc. And that's the idea. And so here is some actual code in the language processing. I'll include the code in the comments. For some reason, I can't include code in the description because it doesn't like brackets. So I'll put it in the comments and pin the comment. But in any event, so whatever language you're using will have, different methods to create and write to a text file. In processing here, you need to create a writer. And then remember, we wanted to, or we always have to, the first line is always solid with a name. And then the last line is end solid. And then just in processing, in order to close your text file, you need these 2 commands. But in the middle, we're going to send out our triangles. And so here we have our R loop going from 0 to 2, and we have our T loop going from 0 to 2 pi. And as described, this will be the first triangle, and this will be the second triangle before moving on to the next T. And in that way, you send all the triangles to the STL file in the proper format. And we can take a look at the result. I'll run it. And we will check out what we get. So first, let's look at it just as a text file and see what it looks like. We'll open it with Notepad. So again, starts with solid, like just as we wanted, and it ends with end solid. Okay. And these are all the triangles that we sent out. Each one between facet, normal, and end facet. You have outer loop, and you have end loop, and you have the vertices. Okay. Notice too that there are no spaces between the lines, and there's no indenting, but that's not going to matter. So let's look at it in using a 3D viewer. Well, there it is. That's exactly what we wanted. Let's look at wireframe, and you can see the triangles, the individual triangles there. So that's exactly what we wanted. One thing I kind of glossed over in the STL format that I showed you, everywhere it said facet normal, I just put 0, 0, 0. And that works most of the time. But what really should go there is a unit normal, a unit normal to the triangle that you're in that facet. So how would you find that? Well, if you remember from vectors in math class, you can get two vectors. Say v is 0.1 minus 0.2. W is 0.3 minus 0.2. To get a normal vector, you take the cross product of that and the direction of it. Remember, there are two normals to a triangle. They point in opposite directions. So this one would be given by the right-hand rule. I think I've drawn it incorrectly here. Here I have the normal sort of pointing up, but I think, and I have negative n here, but I think that should be reversed according to the right-hand rule. It also wants the unit normal. So in order to get the unit normal, you'd have to take that vector you got from the cross product, divide it by its magnitude, and then you get a unit normal pointing in the direction given by the right-hand rule. That's fine. But the good news is you don't really have to worry about it. Although you can do this pretty easily in most programming languages. Most programming languages have cross product. It has a way to generate the magnitude of a vector. So, I mean, it really wouldn't be that hard to do it. But what is hard is to get it to be consistent, because depending on the points you choose, you get different vectors. And so the unit normal you get might not be pointing in the same direction as, say, the neighboring triangle. And it's kind of hard to get it consistent. But the good news is you can put 0, 0, 0, and it doesn't matter for most things. Most programs can read in that file fine. And as a matter of fact, if you really need it, you could use one of the mesh editor to generate the normals and then save it. And so you can get a mesh editor to kind of do the work for you later, after, as a second step. But as I said, it doesn't really matter usually, except the Wikipedia page mentions something about SolidWorks wanting that normal vector there. So it may cause problems if you try and read in an STL file with 0 normals. It may cause problems in SolidWorks, but I don't know anything about that. However, there are ways around that. You could, in a mesh editor, you could open it up and then save it as another file format and then open it up in SolidWorks, open that file up in SolidWorks. So I'm sure there are ways around it, but just so you know.